But she spells it with a Y instead of an I. Oh yeah, I have a friend who spells it with a Y. Okay, that's you. And then yeah, you can just wow. There you go. Make sure you also do it on next week. Very old. Excuse me. What computer is this? This is a Surface Book Pro 2. Yeah, Windows. It's nice. It's actually you can detach the top off and it can be a tablet. Oh, like what? Charger? No, I have a charging brick. I don't know if this works, but I don't think it does. I have this. Does this have charge? 3? I don't know if it works though. That wire might not work. It does? Why doesn't it work for my phone? What? Excuse me. That little thing. Okay, that's cool. It's too old. Well, my computer is new. Actually, it's a year new. Now they have a 3.
Okay, are we ready?
Yes.
Yes.
I'm ready when you're ready. Okay, so we covered the reactions of benzene, and to quickly review them, we had first was the halogenation. So you have the benzene, we burn it with Br2, the presence of NBr2, to brominated benzene. And what did we say about this reaction? What should you know about this one? What are their limitations or the problems or the things we have to be careful about? Two reactors. So what do we do? So this adds in excess. Okay, the benzene must be in excess. The second one was nitration. And you take benzene plus nitric acid in the presence of sulfuric acid, and you get nitration. Now, what is the limitation with this?
You can't use function.
Is it NO2 or NO3? NO2. One thing I forgot to mention. So this has a limitation because also it competes with sulfonation. I forgot to mention something. If you remember, I showed that nitric acid compared to sulfuric acid. So sulfuric acid is the one that's stronger. So the question is why? Why is sulfuric acid stronger? Because these little details will help you remember things. Like why is sulfuric acid slightly stronger? The answer is, once you see here, we showed that the lone pair of the oxygen takes the hydrogen and this opens. Okay? So this has 4 oxygens. So what's the structure? It's SO2OH, O minus. What does this structure has that is interesting? Resonance, how many resonance forms you can write, and also that negative charge will be distributed into all these. Whereas if we write the negative form of NO3, plus, this is minus. You see which one is more stable. This one is more stable because that extra negative charge is distributed around these three oxygens. So sulfuric acid is a stronger acid because it gives you a more stable conjugate base. Nitric acid is strong, but you see you have two negative charge here for a positive charge. So the distribution of two electrons on three oxygen is not as good as one electron on three oxygen. Is everybody understanding this? Here we have one additional electron and it's going to be moving around three oxygen. So it's more spread out, so the substance doesn't feel its negatives, it's very stable. Whereas here we have two extra electrons distributed between the three oxygen because you know how you write different resonance forms for anything. So sulfuric acid is always a stronger acid than nitric because it gives you a more stable conjugate base. And that's why here, you're not only going to get nitration, you're also going to get sulfonation. So in here, the problem is very reactive. In here, it competes with the sulfonation.
So low percent.
So is everybody understanding this? The reason I mentioned this part is I forgot to mention it last time, but it's going to come back many times over, okay? So that stability of the resonance form, especially in chapter 18 and 19. So these two chapters are very important because they involve benzene, which is conjugated. So conjugated forms are important to remember. If you're asked to explain why, there's a good chance things are stable because of resonance. Okay? So then the next one was the sulfonation. So you have the benzene and H2SO4 produces this. So what's the limitation with this one?
It's reversible.
It's reversible. So of course you're not going to get good percent yield. And the last one was Friedel-Crafts. And this one, you have alkylation and acylation. So what's the problem with the alkylation? Always
Rearranges. It will always be arranged.
Rearrangement. So here you're going to always have a rearrangement, which is not a good thing. And what's the problem with acylation? Complex will form, so you need to add water. So this one, you can form a complex, aluminum complex. So you need, don't forget to add water, okay? And what happens with water? Water is polar, benzene is non-polar, so it kind of creates some other issues in terms of solubility. So your reactants are not going to be as solid. So this is a review of what we did last time. But there's a little addition to that alkylation that we're going to mention again later, but I want you to remember anyway from now. It's on chapter 11. So what do we do? How do we do alkylation without rearrangement? So for that, you do what we call coupling, okay? So here, if you want to avoid rearrangement, we're going to do coupling. So coupling will be chapter 11, okay? But you still need to know the overall reaction. So what does it mean coupling? You start with benzene that has a halogen, then you add an organoboron. So like here you can put the chain alkene. So if I want this and I don't want it to rearrange, I use this one with boron like this in the presence of palladium catalyst NOH minus. So this is called the Suzuki reaction, which you're going to do in lab. Okay? So what do you get? You get this. You get an alkylation without rearrangement. So if you don't want rearrangement, you do this reaction. Okay? The good news is you don't need to know the mechanism because it's still kind of like not very clear. But you have to know that if you want in synthesis to add an alkyl without rearrangement, this is the best approach. Another approach, so this is one of them, and they're both coupling. The second coupling method is using an organocuprate. So we use the same thing, benzene that is chlorinated, and we use an organocuprate. So for example, CH3, CH2, CH22, CuLi. This is called an organocuprate, and it produces this. So these are the alkylations without rearrangement. Okay, so I'm not writing everything, but I'm just showing you that you can have an alkylation. You have other options for alkylation without rearrangement, and we're going to study them in chapter 9. But it's good to have a first exposure so that when we come back, you reinforce it. So of course, this needs other reactants with it. I'm not writing all the products, so I'm just leaving it like that, but there is some other product in this process. So this covers all the reactions to make a substituted benzene, meaning one substituent on the benzene. But there are some other reactions on the substituent. So how do I know if I have a reaction that is happening on the benzene or on the substituent? The answer is very clear. These are the only possible ones on benzene. So if you see anything else, it means it's not on the benzene, it's going to be on the substituent. So I'm going to give you a list of them. So here's an example. So here, these are reactions of substituted benzenes. So what is a substituted benzene? It's a benzene with a substituent. It's not just benzene, it has something on it. So for example, the first type of reaction can have substitution. So one example is if I have my alkylated benzene and if I use here bromine in the presence of light, what does it remind you? Which chapter is that? Radical. So it's a radical reaction. Now, the question is, where is the radical going to form? You know how we first remove an H? The H is going to be, the bromine will substitute an H. Which one will be removed? Is it this H, or this H, or this one? That's the key thing. No, radical means you'll remove an H and you're left with one dot on that carbon. So which one will form? Is it this one that will leave, or this one, or this one? It's this one because what? Because it will be conjugated. Okay? So normally you end up with a radical like this as an intermediate. And that radical can be conjugated with the ring. So conjugated, it's always next to the benzene ring. That's the one that's more reactive. And then you end up with, so we don't go back to the mechanism because you already know it in chapter 12. So this is chapter 12, except that the alkene is attached to a benzene ring. So the benzene is so stable that it's just sitting there, just hanging out, not paying attention to what's going on. But it stabilizes this one, okay? So if I see Br2 with light, it's very different from Br2 with what? Fe, Br3. You see the Lewis acid, it means the reaction is on the benzene. But if you see just light is not enough to make the reaction happen on the benzene. Okay? Next one, you can also do this. So what is NBS? What does it remind you? So it's N-bromosuccinimide, which is also bromination. So anything that's not the 5 there happens on the substituent. So this is chapter 10, this is chapter 10. I'm sorry, chapter 12. They're both radical. Actually, the catalyst here is peroxide and heat. So for substitution, I have many of them. So this is A, which is radical reactions. So these are 2, A and B. Okay, they're radical. Then you have this one. This is a substituted benzene. So of course, how did we produce this from this? So this is to show you some of the synthesis that's going to happen. How do I produce this from this? Once I have this, I can add bromine and I can do other stuff with it. Same thing here. I could produce this one, and then if you put OH minus, what's going to happen here? Substitution. Why? Because this is a nucleophile, this is a nucleophile. The OH minus is never going to touch the benzene ring because they're both nucleophilic. So what you're going to end up with is CH2OH. So you should know these things. We don't need to teach them again because that's substitution for chapter 9. So all of these things are, whatever you learned before will still apply. What if we put Cn minus? So that's also a nucleophile. So it's CH2Cn. I'm talking about the same reaction. Any nucleophile you can think of would work. So I can also put NH3. Another one is, let me take this. So what if you put OH minus here? What's the difference between this scenario and this one? What is called what? Substitution always competes with what? Elimination. So in this case, which one would be favored, a substitution or an elimination? Why? What is going to be eliminated here? It's going to be H and Br. So you end up with CH, CH2, CH3. So why is this favored rather than a substitution? Conjugated. So this is a conjugated product with the ring, so elimination is favored. Here we don't have elimination because we don't have two atoms to be removed. So remember, every time you see substitution, it always competes with elimination, and if your substituent is on the benzene ring, there's a good chance you're gonna end up with an elimination. So this is chapter 9. Even if it looks in a different chapter, it's still chapter 9, but the only added thing here is that the benzene ring adds that conjugation, which favors certain products. Okay, so all of these are substitution. This is elimination. And again, why is elimination happening? It's because it is conjugated. Then we can do reduction. So what is reduction? Means you add hydrogens. That's what means reduction. A molecule, you add hydrogen to it. So if I take that compound, let's say, and we add hydrogen in the presence of PDC, what chapter does this remind you? Chapter 6 or 7, which is the alkenes. So we're going to look at it as an alkene. So this is hydrogenation. So what is going to be hydrogenated? This. Can we hydrogenate the ring? No. Why not? It is aromatic. If you're going to add hydrogen, you're going to remove aromaticity. Aromaticity is the most important thing. So here, when you do this, you're going to end up with the alkene. With the alkane, I'm sorry. Sorry. Another one. So here, an alkene, which is chapter 2. If I take now this one, so all of these are, of course, reaction of substituted alkene, benzenes. So what if I do hydrogenation here? Same thing. This will add to the triple bond, but the only difference is you need a different type of catalyst. So in this case, you would need radium nickel. Okay? And then you end up with what? If you're going to reduce, it means all the multiple bonds become single bond. So you're going to add hydrogen, so it's going to be CH2, CH2, and H2. So we keep adding until you have no more pi bonds. Now, can we really reduce the benzene ring? No. What does it take to create magic? You need a lot of pressure. That's why sometimes you need some pressure to create magic. You're not going to create magic with low pressure, believe me. So here, you need a lot of pressure and you need high temperature. For this case, if you want to hydrogenate the benzene ring, you can, but it's going to require very special conditions. So what are the special conditions? High temperature and high pressure. It's not enough to put high temperature. And for this, you need nickel, you need 250 degrees Celsius minimum, and you need 25 atmosphere. You understand what 25 atmospheres represent? It's huge pressure. So that will make the benzene turn into a cyclohexane. So remember, if you see reduction, usually the reduction happens on anything that has double bond, triple bond, rarely the ring. But if you really want to touch the ring, you have to do very high temperature and very high pressure. So what else? What is missing? We studied substitution, we studied elimination, we studied reduction. What is the next one? Oxidation. And you can see all of these don't fit in these. You agree? So it shouldn't be an issue. If you see something you saw before, the ring is just there, hanging in there. That's all. So don't be distracted. It's just a distraction. It's not the focus. The focus is always, I'm only going to focus on the ring if I have these 5 reactions. That's it. So let's look at oxidation. So, and you start to see that everything you learned before, you can't forget. So if you forgot or you didn't use this textbook, please go back to the previous chapters. And I mean it, you really need to read all the other chapters, no exception. You have to refresh a little bit, like maybe not so much the first 4 chapters, but definitely 5, 6, 7, 8, and 9 are a must, you know. Okay, 5, not so much. I would say from 6, 7, 8, 9. 6, 7, 8, 9. You have to read them. Okay, so what's left is oxidation. Okay, so the last category is oxidation. And of course, all these will happen on the substituent, not on the ring. It's on the substituent. So here we go. If I have the last benzene that I put, this is toluene, okay? And I put chromic acid. By the way, what works with chromic acid works also with permanganate. Chromium and permanganate are very strong oxidizing agents. So the book sometimes uses this, sometimes uses permanganate, so don't be surprised. And if you read some other textbooks, some people prefer to use permanganate, some people prefer to use chromium. But they're the same. If you see any one of those, it's an oxidation. So what is oxidized? Can we touch the ring? So what does it mean, oxidation? You're going to add oxygens. And you can add as many oxygen as you have hydrogens. Okay? So you see we have 3 hydrogens here. So you end up with benzoic acid. 3 bonds with oxygen, it means almost like 3 oxygen atoms. It's not literally 3 oxygen atoms, but it's 3 bonds with oxygen. Okay? Next one. What if I have this? And I do use chromic acid. Still, very strong oxidizing agent. Which one will be chopped off? This comes out, it's still going to give you the same product. So it cuts all the way to here. No matter how long the chain is, it's still going to end up with benzoic acid. Why? It takes the hydrogen with this, makes formic acid, takes the hydrogen from this, makes another acid. So it cuts everywhere there are hydrogen, it will make oxygen. So the chain will be cut. Okay? Now, what if we have this? And I'm going to put CH3 here. Why not? Everywhere, you're going to have complete oxidation. That's to show how powerful chromic acid is. Wherever there is a CNH, it's going to cut it. The last one Now notice, this is primary carbon. Agree? This is secondary carbon. This is secondary. This is primary. We're talking about the carbons, how many carbons they're attached to. But this one is what? Tertiary. Sure. That's the only time it doesn't work.
The fourth.
It's quaternary, but if we forget the ring, I'm only focusing on this, yes. So it's quaternary, but there is no H on that carbon. Okay? So if there's no H, no reaction. Here. Okay? So remember, no reactions if you don't have an H on the carbon next to the ring, right next to the ring. If I had a CH2 in between and this, then it would cut on the CH2. Okay? That's clear. So oxidation happens all the time except for the carbon that has no H. Keep in mind, just like the alcohols, if you remember, primary alcohols, they oxidize, secondary oxidize, but tertiary don't oxidize. It's because we need an H in that position. Okay, another one. So we're done with oxidation. Then, I'm kind of debating, there's two parts here. Yeah, so there's another type of reaction that is important, is how do we make a lot of substituted benzenes that are not these? You understand? Here we had bromination, nitration, sulfonation, alkylation. What if I want to put something else that's none of this? How do I add it to the benzene list? So these are very, very important reactions, and we use arene diazonium ion. So the arene diazonium ion is a huge part of synthesis that you use to make any kind of substituted benzenes. Because you see, all of the ones I used, this was, you could use Friedel-Crafts and then bromination, whatever. This was, after you do Friedel-Crafts, you do elimination. So it's kind of using any of the five there to first start with the first reaction. But there are many other ways you can make this reaction happen very quickly, which are using the arene diazonium ion. So these are a huge part of organic chem, and some textbooks will have like a full chapter just on this. We don't do a full chapter here because it's a little bit old style chemistry. This was like in the early 20th century. It's still used, but not as much as the new method, like coupling. So you need to know it, but it's not the most important part of organic chem. So what is an arene diazonium ion? It's this. So substituted benzene is making other substituted benzenes. So here is the arene diazonium ion. It's N, this is plus, and this is an ion, so it's usually with Cl minus. Okay? So this compound is a diazonium salt. So if you look closely, if I can get this out of the way, what does this become? This comes off like a substituted with something else. What does this become once it's out? It's N2, you agree? And what is N2? Gas. So that's the reason these reactions are very good, because in the end, they always produce what? A gas, and that drives the reaction. So if you start with this, you can do so many type of reactions. Okay, so I'm gonna give you a series of them, and then I'll show you how do we make this diazonium salt, first of all. So how you make diazonium salt, it's because on my note, they're like a little bit off, not reading the order. So what you do to make this, you have to have benzenamine. Okay? And we'll figure out later how to make it. So you start with benzenamine, and if you see NaNO3, NO2, I'm sorry, so sodium nitrite, not nitrate, NaNO2, in the presence of HCl, and at 0 degrees Celsius, you will produce the diazonium salt. So you don't need to know the mechanism. All you need to know is that's how you make the diazonium salt. Okay? So if you want to put any substituent, start with benzenamine and then make the diazonium salt. Then what are the reactions there? So I'm going to pull some of the reactions. Skip them. Okay. Here we go. So I'm going to put some of them here. Actually, I have only 3. So if I start with this one and use CuBr, so this is cuprous salt. What's going to happen is you get the brominated compound plus N2 plus CuCl. So you see, this is really easy. Now, if I use, starting with the same reactant, CuCl, of course you're going to find it chlorinated. If you use CuCN, you're going to end up with so all of these, whenever you see a copper salt, so this is very important to pay attention to these. These are called cuprous salts. So if you see cuprous salts, you're going to end up with a substituted benzene. That's really the reaction is driven. And these are called the Sandmeyer reaction. So I don't want to write all of them, but anywhere you see a cuprous salt, starting from the diazonium salt, that's called Sandmeyer reaction. So that's the key thing. I'm putting everything in red for you to focus on the part that's important. Okay? Another way also of using this cuprous salt that are not Sandmeyer reactions. So that's one aspect. Another one is where the old method, that's when Sandmeyer found out this, I think he got a Nobel Prize for this. Because any reaction that has a name, it means it really made huge impact on the progress of organic chem. So here we have another one where I can use this diazonium salt. And I have a substituent on the ring. It could be CH3. So one way with Ki. All you need is Ki. You don't need any fancy reactant. And automatically, you're gonna end up with iodine here, NCH3, plus N2, plus KCl. So it's a kind of a salt exchange kind of reaction. Another one, if I take this, sorry, N2. And I can add a substituent or not, who cares? Because the reaction happens on the N2 part. So here, if you use HBF4, which is a Lewis acid, but it has too many atoms, okay? So it's H minus and BF4 plus, or something like that. You're gonna end up with fluorination plus BF3 plus N2 plus HCl. Another one is, so you have many of these in your book, just look at them. So if you just protonate, just use an acid there, you don't even need to use any of the fancy stuff. And then you end up with no H, actually, plus N2 plus H2O, HCl. HCl. So I'm not going to write all of them, but there are so many of them in your book. Just to understand, whenever you see a diazonium ion, you're going to have the N2 leave, and you're going to have a substitution.
Would the same reaction still work if there was a another substituent?
No, if you have,
Like if there's a methyl?
no. It has, oh yeah, if there are any substituent on the ring, it doesn't matter, it's the N2, the diazonium that matters. Yeah. Whether you have a substituent or not, the reaction will always happen on the nitrogen site, okay? So these are all the reactions of substituted benzene, okay? But all these reactions are on the substituent, you agree? So the question is, what if I want two substituents now on the benzene ring? I used one here. How do we make this, okay? How do we make a compound that has more than one substituent? And especially if I want them different. So not only do we need to know how to put a substituent on the benzene ring, but then can we add a second substituent, a third substituent? And where would these substituents end up? So that's the second part of this chapter, is to understand how to add a second substituent. And where would that substituent land? In what position? And for that, we're going to look at, you have to start with the substituted benzene. You understand? So you start with the substituted benzene, and then you add the second substituent. So I'm going to use a few substituted benzenes and explain a few things based on that. Hopefully, you will follow me and understand what I'm talking about. I just want to make sure I don't miss anything. Sorry, because I know the lecture notes are slightly different from what I wanted to say. Okay, so I think I know where I am. Now, if you have one substituent or two or three, to touch the benzene ring, you always need what? What adds to the benzene ring? Has to always be an electrophile, because the benzene ring is always going to be a nucleophile. So let me look at this one. The starting material for response. So imagine I start with this. I want to add a second substituent. So before I even add a second substituent, I want to know where would that substituent land. And for that reason, you have to now know how to write resonance forms. So this substance has resonance forms. So you have a lone pair that's conjugated with the ring. So which way are the electrons going to come out of the ring, or these will go to the ring? Those will go. So this can give the pair here. Will it change its, how many pairs will be around the nitrogen at that point? If I move this pair here, how many pairs of electrons are around the nitrogen? Around the nitrogen, how many pairs of electrons? Well, if I move it here, how many are around the nitrogen?
0.
4. 2 here, 3, 4. These are pairs of electrons. Yes or no?
Yes.
That's what I mean. Pairs of electrons around the nitrogen. But what's going to happen to this carbon now?
Negative.
How many pairs? Don't tell me double bond. 5. Is that going to work?
No.
So what we now need to do is take a double bond and put it on that atom. Okay, so my first resonance form, and if you don't know, by the way, how to write resonance forms, you need to go to the tutorial, which is on page, please write it down, and you have questions there that are answered, so you can check and see, and it's page 382. Page 382, you have a bunch of questions there that you can practice. So what do we have? So now this is negative, okay? And we have a double bond here, and this is positive. What's next? Are we done with the resonance form? What's the next step? This makes a pi bond, this moves here. And notice, guys, you either move electrons to make another bond or to make a lone pair. If I'm moving a lone pair to make it a bond, I have to put it between the two atoms. And you might say, this is obvious. Well, on your test, if you don't show me correctly, if you just throw arrows halfway, stopping somewhere that I'm not understanding, then you're not understanding what you're doing. And these two electrons have to land on this atom, not here. Why? If you don't know why, you don't understand how you're doing it. You can't keep moving electrons. You just move it one at a time, one step at a time. Well, if I move these here, I have to move these here, and it's like, you're not going to get the resonance forms that are intermediate, So you can't move it here because it will be too many bonds around this carbon. So you have to sit on that carbon because it will still end up with 4. You agree? Yes. But this one now, it will be with 4, but it will be negative, but that's okay. It still has an octet. You can't put more than an octet in all your resonance forms, no matter what. Okay? So we have this. Now this is negative. The double bond is here. And I'm sorry, the double bond is here and here. And this. Next time, I'm not going to keep them next to each other, like high school. You know why? Because I know now you're talking to each other all the time. Later, you're going to ask me, wait a minute, what happened? Please, if you have a question for each other, ask them to me first. Because the more you get distracted, the less you're going to learn what's going on, and it can be a distraction for your classmates. Believe me, you will thank me for this. Okay, try not to sit next to each other, it's better. Okay, so then you go here, and this goes here. And then we have the next one. Now, starting from this chapter, you have to know how many total resonance forms you have. And I know some of you learned it with Wayne. He pushed this a lot from the first day. With me, we didn't do much of it. We did some, but not enough. But here we have to do a lot. So the last step here is this comes back here, this goes here. Then I know I'm done because the electrons landed on my first original atom. And by the way, the number of resonance forms determines the stability of the substance. So the more resonance you have, the more stable it is. So if you can't write all of them, you're not going to be able to compare which substances are the most stable. Okay? So that's one. Now I'm going to try this. How about this one? So how are we going to move the electrons here? First of all, what is the driving force to move electrons? It's always a polar bond. In here, the polarity is on the nitrogen is different from carbon. Which bond is the most polar here?
Oxygen.
I said bond, I didn't say atom. If I say which bond is the most polar, you have to tell me a bond, not an oxygen. Oxygen is not a bond. So which one? C double bond O. Now, if it's polar, which way should the electron move? Away from the oxygen or towards the oxygen? Yes. So this has to move in here. So what happens automatically? This moves here. Okay? So our first resonance form is this. O minus H. And then I have a double bond here, but now this is positive. Do you see? Then what's next? This comes here, and then we have a double bond here, double bond here. What's next? One more time. And then, are we done? I'm missing a double bond here, sorry. So then the next step is this moves here, but if this moves here, this carbon has no longer an octet, you have to move this back. And then you end up with the last resonance form, which is okay. Yes.
Why don't we show the intermediate stage like we did on the ring? Like, why didn't we show a period where the carbon was positive?
Which
So the last step you just did, you moved the double bond and made a double bond at the same time. But in all the other ones, you only moved
because
the
you
double
can't
bond.
have a carbon that is positive next to an oxygen that's negative.
Okay.
If you have electrons to move, you have to move them.
Okay.
You have to. It's a good question. So this is why you need practice, okay? Now, if you look at the top versus the second, and I picked these two on purpose, look at where are the arrows on the top, the first step, where are the arrows going? They're going towards the ring. So what does it mean? We're adding what? More electrons to the ring. How about the second one? We're moving away. Now, what are the reactions that happen on the ring again? Can you remind me? What type of reactions can we do on the ring? What are they called? They're all what? electrophilic substitution. All reactions are electrophilic, meaning what? We need to bring what? Something positive or something negative? So which one would work better? The top or the bottom? If you're going to bring something positive to the ring, which one is better? Top scenario or the bottom scenario? If I bring something positive, will it attach to this?
No.
It's the opposite. If it's, you can't bring something electrophilic to something electrophilic. What are called again? All these reactions are called what? So what does it mean, electrophilic? It's because the benzene is what? Nucleophilic. So in these two scenarios, which one is more nucleophilic, the top or the bottom?
The top.
The top. This is more nucleophilic than the benzene ring itself. Why? Because we have what? Negative charge. So this substituent, NH2, is adding electron to the ring, so it's making it more reactive. Okay? The reason the ring doesn't want to react, it's because it has what it needs. So if you add more electrons, then it's going to be more negative, so it wants to get rid of that more negative, so it becomes more reactive. So making the ring more negative means making it more reactive. So that substituent is called activating substituent. So anything that makes the reaction go faster, it activates it. So NH2 is an activating substituent. But in this case, what does it mean, activating? What does it mean to activate the benzene ring? Donating, meaning making it more negative. So this is important to understand. A substituted benzene like this is more reactive than regular benzene. Okay? So NH2 right here is an electron donating substituent. ED for electron donating. And in this case, it's electron donating by resonance. And we started this in chapter 2, if you remember. My student 231, we did it in chapter 2. We looked at electron donating versus electron what? Withdrawing. So what happened here? This is electron withdrawing by resonance. So NH2 is an electron donating by resonance. COH is an electron withdrawing by resonance. So for benzene, every time you have an electron donating, it is what? Activating. So electron donating substituent are activating. But this is the opposite. We don't call it deactivating, but it's not activating. Okay, non-activating. Is everybody clear? So if you have a substituent that donates electron to the ring, it's making the ring more reactive. And what does it mean, more reactive? More nucleophilic, which means more reactive with what? Electrophiles. Now, where would that electrophile attach on the top scenario? Which positions are the favorite one based on what you just wrote?
Where it has the charges.
There's a negative charge because you bring in something positive. Where is it going to go? It's going to go straight from that negative spot. So where are the negative spots? This, this, and this. So the two positions next to the substituent, this one and this one, are called ortho positions. So this is an ortho position. So why is it the ortho position? That's where the reaction would happen, because that's a center that is negative. This position is called para. Okay? So if you have, let's summarize this. If we have an electron donating substituent, what is it going to do? By donating its electrons, it's going to increase what? The reactivity, because it increases what? The negativity or the nucleophilicity of the benzene ring. So an electron donating substituent adds electrons to the benzene ring. And if it adds electrons, it makes it more nucleophile, which means more reactive. Is everybody clear? Electron donating means adding more electrons to the ring, which means more nucleophile, which means more reactive towards what? Electrophilic substituents. Okay? And then the last thing is, where is the reaction going to happen? It's not going to happen everywhere. It only happens where? In the ortho and the para position. Why? Because these are the only spots that are negative. Is everybody understanding this? Okay, now we look at electron withdrawing substituent. I'm going to use a different color. So if it's electron withdrawing, what does it mean? It means it is not allowing the ring to be what? Nucleophilic. So they're deactivating. They're deactivating. They're not going to allow the reaction to happen. They make it very difficult to happen. And what are the positions that are impossible to add an electrophile? Can I add an electrophile in this position?
No.
Why?
It's already positive.
Can I add here?
No.
Can I add here?
No.
So what is left? What is not positive? The only positions that are not positive are, as you see, this. See these two positions? They're never positive. You see? The other positions can be positive. So these are called meta. So an electron donating makes the reaction happen in the ortho and para. An electron withdrawing makes the reaction happen in the meta position. The other thing is the top one will happen very fast, and the bottom one will be what? Extremely slow, and will get you very bad percentage. Okay? So now, if you look at your book on page 887, it's very important to see this and to try to explain that on your own at home. See, write all the resonance forms when you add these substituents. So what it shows you, the top ones are very, it says orthopara directing, that's what the term we use, orthopara directing means the reaction happens in these positions. And these are the activating substituents. So the top of the table are activating. The bottom of the table are deactivating, meaning it only happens in the meta position. And you don't have a book in front of you, too bad, because I need you, next time you really need to bring a book, you have to, okay? Starting from Tuesday, I'm gonna go over, Monday, we're gonna go over problems. You have to have your book. But look in the middle of that table. You see where it says weakly deactivating? What do you see there? Do you see the colors? How on the top of the table, the gray shaded area has the same color shades. You agree? And if you look at the bottom part, the gray shaded area have the same shade. You see that or not? But in the middle, what do you have? You have weakly deactivating, that's light, the very light gray, and the other side, that's darker gray. So what does it mean? So for these halogens, they tell you they're weakly deactivating, but they're in what position? Normally deactivation should only happen in what position? Meta. But these only exception, they're not gonna happen in the meta, they're gonna only happen in the ortho and para. So learn how to read this. So halogens, they're definitely deactivating, but they only direct the reaction in ortho and para. So the question is why? And I'm gonna explain it, and I expect you to know why, okay? So I'm gonna use a halogen, the three of them, actually, and then I'm gonna use another one that's kind of in between. So everybody understand these. What is an electron withdrawing versus an electron donating and how they direct the reaction. So let's try with a halogen. So I'm going to put F. Without looking at your book, what does F do? We already learned something about fluorine that's exceptional compared to all the other atoms. What is F? It's the smallest atom that is reactive. That's not a noble gas. Of course, hydrogen is a different story, but outside of the noble gases, fluorine is the smallest. So what does a small atom do? Will it give away electrons or gain electrons?
Give away.
Really? Small atoms, what does it mean small? The electrons are, where are the electrons? Close to the nucleus. So can they fly away? What is the nucleus going to do? Hold them. So fluorine is the smallest atom. So that's the reason fluorine can only add electrons. So what is fluorine then doing? Is it an electron donating or an electron withdrawing? It's withdrawing by inductive effect. Remember, so if you don't know this stuff, go read chapter 2. So fluorine, right here, it withdraws. So the arrow there is withdrawing. It's an electron withdrawing by inductive effect. Inductive means like just a push and pull, no resonance involved. Is everybody seeing this? So fluorine is definitely withdrawing. So that makes it what? Activating or deactivating? Deactivating. But at the same time, fluorine can be electron donating by what? What effect? Resonance. So I'm going to use the green by resonance. So it can go here and this goes here. So not everything is black and white. Not everything is either or. There are things that are both. And this is the scenario where we have both. So fluorine here is electron withdrawing by inductive effect, but also electron donating by what? By resonance. So the green stuff shows electron donating by resonance. The question is, which one is stronger? Is it donating or withdrawing? The reality is it's withdrawing. Definitely it withdraws stronger than donates. But because it does the resonance effect, it opens up the ortho and para. You understand? Because it can give electrons. That's the reason it will be ortho para direct. Okay? So it does both. It does withdraw and donates. So if it donates, it opens the ortho and para. If it withdraws, it only withdraws, it just pulls on the electrons. It weakens the pull, but it doesn't really necessarily have a specific, it's not by resonance, you know, so it's just kind of pulling a little bit the electrons from the benzene ring. But it's not literally creating resonance there. It's not conjugating things. Whereas on the Donating, you have different resonance forms. Do you understand? So an inductive effect only pulls, but there is no resonance form to be written. Whereas an electron donating by resonance, there are resonance forms to be written. So the only resonance form you can write is with negative charges here. But at the same time, this is pulling, meaning the negative charge here is not as negative as we want. Do you understand? Because it does both. Now let's try this. This is where it's extremely important. You understand what I mean? So what if I put chlorine, which is after chlorine? Is chlorine electron withdrawing?
Not as much as fluorine.
Not as much, but it's
Yes.
still electron withdrawing. So if I put 3 arrows here, I'm probably going to put maybe 2. But it's still electron withdrawing by inductive effect. I for inductive. Okay? Is it electron donating? Can we write resonance forms?
Yes.
Yes. So we're going to write this one. But why do we have resonance forms? What does it mean when you put the arrow? What's moving? When you put these arrows, what's moving? Electrons. And where are they moving? They're moving from one orbital to the next. Do you agree or not? Now, let's go back. What orbital is this?
2p.
2p. Thank you. I just want that word. That's it. I just want 2p. What is this on the carbon? What is the orbital it's moving to?
sp2.
So it's also what?
2p.
2p. The fluorine has electrons in its 2p. The carbon has electrons in its 2p. How about here? Where are these electrons?
3p.
And where are they moving? Is that a good transition?
Yes.
Absolutely not. One is big, one is small. It's almost like, you know what happened in electricity, you heard about resistance. You have electron jumping and falls into a hole, that's what resistance is. Here, it's almost falling into a smaller space. It will happen, but it's not a very good deal. They have to hop from one orbital to another of similar sizes. So what does it tell us? It tells us, yes, it's definitely electron withdrawing, electron donating by resonance, but it's not a real good resonance. You understand why? Because the electrons are hopping from what to what? From a 3p to a 2p. So it's not as good as from a 2p to a 2p. You know, it's almost like me asking you to walk from one step to another. If I keep the same pace between the steps, the same height, you'll be fine. But if every now and then I give you a bigger gap, it's going to be hard to kind of jump back and forth. And resonance means they have to go back and forth. It might jump down, but it's going to be hard to jump up. And literally, I want you to visualize it that way. The electrons are literally jumping from one space to another. So if you don't visualize that, I mean, when I talk about this, I already can see them hopping around like little rabbits jumping from one place to another. So that's what it is. It's like they're jumping. So 3p to 2p is not a good deal as much as 2p to 2p. Now, how about if we put bromine?
4p to 2p.
4p to 2p, which is even what?
Worse.
So now let's look at that table and see. You see how they put F on the top? Closer to activating. Why? It's really because it's this particular effect. These, here we go from 3p to 2p. Bromine will be 4p to 2p. So the electron donating diminishes. Okay? It's not as good, so that's why they're less activated. Is everybody understanding this? So what are the consequences? It's like, yeah, fluorine will react the fastest, will give us probably the orthopara. The bromine and the chlorine will react very slowly and they're not the best choice. Is that clear? So that's all. So when it comes to synthesis later, you have to understand, what do I choose? Do I choose a bromine or chlorine or iodine or fluorine? And the reason is these two effects. Another one last substituent to kind of cover a little bit of everything. Because if you understand electron donating, electron withdrawing, and if you understand by resonance or reductive effect, there is another effect, actually, I'll talk about it if I have time. But here's another one, for example. Yeah. This. Whatever it is, there, who cares? So now, what do we have here going on? So you have the nitrogen that can be given electrons, do you agree? To the ring. So we can have, this goes here, this moves here, and then as a result, what happens here? So when we touch this? No. But it's going to be electron donating by resonance. Okay? You can also have this. Oxygen being smaller than nitrogen, of course it's not much smaller, but still. So what can happen, the oxygen pulls, this has to come back down here, and this has to come here. So you see, this particular substituent is both electron donating and electron withdrawing. The question is, which one is a better, is a stronger, is it the withdrawing or the donating? So this is electron withdrawing. That's what makes it kind of low on the activity, okay? So you will have some substituents that are both electron donating and electron withdrawing, and you have to try to explain by writing all the resonance forms. Is that clear?
Yes.
Okay, one last example. So we know electron donating by resonance, electron withdrawing by resonance, meaning the electrons move to or from the ring. Then we know the electron donating by inductive effect, which is the fluorine pulling because it's small, meaning you don't have to write the resonance form, but all you have to understand is like there is a force that is pulling the electrons. The last effect is hyperconjugation. So you have the hyperconjugation effect. And when does this happen? So if I have a benzene ring, I'm going to represent it like this, draw it like this. So these are the pi bonds. So you see what I'm trying to achieve here, that it's perpendicular. And what if I put a CH2? You see this bond, the angle here is 109, but it's not too far from a 90. Okay? So if it's not too far from a 90, this hydrogen can keep hopping back and forth. So that's hyperconjugation. That hydrogen on the alkene can keep hopping back and forth. So if it hops, it means it's electron donating, it's going to the atom to give more electrons to it. It's basically the whole bond here. That's what we mean. So this pair of electrons pops here, back and forth. So that's called electron donating by resonance, by hyperconjugation. So if you have the CH, the sp3 carbon with an H on it, just like you know the hydride shift, this is kind of similar of a hydride shift. It goes back and forth from the CH3 to the ring, and it fills that orbital. So that's an electron donating by hyperconjugation. So all alkyl groups are electron donating by hyperconjugation. And then we have another one, so that I covered all of them, I didn't forget. How about this? So, what is this gonna do? Yeah,
Sorry, going back to the other one really quickly, with the 109 degrees, was the significance of that just that it was pretty close?
it's close to a 90, because all of these are 90 degrees. The
Oh,
angle,
all of them are 90 degrees.
yes,
I
all the
see.
p orbitals are 90 degrees. So 109 is not like 120,
Right.
okay? So, and since hydrogen is small, it can literally shift. That's really what it means, hyperconjugation. Hyperconjugation is when you have a hydrogen hopping from an sp3 to an sp2, back and forth. How about here? What do we have here? Is this electron donating or electron withdrawing? We can write what? And move this and put this. So allylic compounds are electrons donating by what? Resonance. Okay? So it's electron donating by resonance. How about this? This is my ring, this is the next ring. What can happen here? This can also move here, this moves here. But it's also going to be what? Electron donating by resonance. But it's not a very stable situation, so it's not very donating, it's slight. So the weakest electron donating effects are, and it shows there, arylic, allylic. Do you know the table there where you see it, the weakest electron donating? AR for arylic, this is aryl. This is an aryl. And this is a vinyl. And it says there. So vinyl and aryl are the lowest on the electron donating effect because they do it by resonance, but they're not super stable, especially. It's conjugated, but it's not, it's going to be charged. So I'm hoping that you study this table very well because the next chapter is based on these concepts. So everything builds on the prior chapter. So if you don't understand this, you're going to struggle with the next one. And when are we supposed to start next chapter? Monday or Wednesday? Monday? So, yeah, so pretty much, I'm almost done with this one, but I'm not worried because the next one is easier, much, much easier, because we're going to use the exact same concept and build in the same way. So, except that they're slightly on different compounds. But I'm going to use a day to go over questions from chapters 18 and 19. So we won't have 3 days of chapter 19. We're going to have 2 days, and then the last one will be questions.
Yeah.